Yes, I'm ready. So we can
Yes, please
start,
start.
right?
Yes, you can start.
Okay. Hello, everybody. My name is Alex Matveev. Thank you, Anup, for organization of this webinar. I'm developer of PastaPro software for pipe stress analysis, which is developing since 1965. It's more than 50 years already, but it's very famous and it's standard de facto in Russia and some other countries. Actually, only this software is used. But right now we are on worldwide market and we also sell our software for worldwide customers. So now we have a webinar about the pipe stress analysis of the thermoplastic piping systems. It's HDPE, PP, PVC, and some other thermoplastic materials. Before we start, just brief information about the software. It's developed in 1965. We have more than 3,000 active users, more than 10,000 licenses. And the user interface and documentation is on three languages, English, Chinese, and Russian. And we have 32 piping codes. We have 18 codes for wind, seismic, snow, and ice loads. It is used in different industries. It's process piping systems, oil and gas pipelines, district heating, natural gas, water, and pipe generation piping, power piping systems. Actually, we have several software. PAS, it's developer of different software. First one is the pipe stress software. The second is the nozzle stress intensification and flexibility factor calculation software. It is PAS Nozzle FEM. It can calculate the nozzle flexibilities using finite element method, nozzle allowable loads, nozzle stresses, and also it can calculate the stress intensification and flexibility factors for tees, for non-standard tees like lateral tees, for example, for trunnions and other elements. And it is smoothly integrated with StarProf. So you work in StarProf interface and it automatically call the nozzle FEM software on the background and calculate for you the flexibilities, stress intensification factors, and so on. And also we have a hydro system software for hydraulic analysis, and also it is integrated with StarProf software. It can calculate the slug flow loads on the piping systems and transfer that loads to StarProf stress analysis software. And also we have water hammer analysis in hydro system. It also can transfer the loads to StarProf. And also we have the PAS equip software for pressure vessel, tanks, columns, heat exchangers, analysis and design. So we have all the software for example, oil and gas industry. And this is the codes that we have, including the code for thermoplastic piping system. It is DVS 2210 and DVS 2205 for thermoplastic piping system. Of course, we have the code for fiberglass piping system, and we have the full scope of codes for steel piping systems. It is all American codes. We have full scope of Chinese codes because StarProf is very popular in China. And we have the full scope of Russian codes because StarProf is standard de facto in Russia and some other related countries. And this is the list of the codes for equipment analysis, for the databases with properties of the pipes, steel pipes. It is the full scope of American codes, full scope of European codes, Chinese codes, and ghost codes. And also wind, snow, ice, and seismic load codes. Okay. Anup, please switch off the microphone. Okay, so also we have online pipe stress training course. Here you can find the discount code. It is course developed by me. It covers all the theory of pipe stress analysis, also the practice with StarProf software, and also it includes the training for the HDPE pipe stress analysis and also for fiberglass pipe stress analysis. Some topics about the dynamic analysis and a lot of static analysis of piping systems. So you can take a shot of this page. I will also show it in the end of the webinar. Okay. So now it is the topic of our seminar. It is the stress analysis of the thermoplastic piping systems. So thermoplastic piping systems can be different. The first one is rigid piping system, and StarProf cover that type of piping system. You can see it here, the rigid thermoplastic piping systems. Also, we have flexible piping systems. Usually, we don't calculate stresses in flexible thermoplastic piping system because it's flexible like hose, and we don't need to check the thermal expansions in such piping system because it can compensate it because of its flexibility. So we only need to check the wall thickness from the pressure, and also we need to check the loads on the end anchors. For example, if this type of piping is buried, we have a special procedure, start elements, and it can analyze the wall thickness and loads on the end anchors for flexible piping, but not in the not in 3D modeling of the piping system model. So the main piping system which we analyze, it is the rigid piping systems. Also some thermoplastic piping have some reinforcement. There are some reinforced thermoplastic piping. This DVS code which we use in StarProf software, it doesn't cover the reinforced thermoplastic piping, but we have experience analyzing such systems using the ISO code for fiberglass piping systems. But developers, manufacturers of such piping should perform tests and provide all the required information for analyzing it using the ISO code for fiberglass piping systems. So now we will talk about the rigid thermoplastic piping systems. What is the main features of thermoplastic piping comparing to the steel piping systems? The first is that allowable stress of plastic piping depends on the service life in hours or years, and on temperature. For example, for steel piping systems, it depends only on temperature, but for thermoplastic, it also depends on service life. So you should define how many years it should withstand, 5 years, or maybe 15 years, 20 years, 50 years, and so on. Allowable stresses will be different. The next is the thermal expansion factor for plastic piping systems. It's several times greater than for steel piping systems. For example, for HDPE, it's about 20 times greater than for the steel piping systems. Also, linear expansion from the pressure load is also significant for such piping systems. So we always should include the Bourdon effect. Because in some software the Bourdon effect is switched off by default, but we should take it into account because its influence is significant. So in StarProf we always take into account the Bourdon effect, even for steel piping and of course for thermoplastic piping systems. So you will see the thermal expansions and the pressure expansions of the piping system. The next is the elongation of the pipes due to the swelling effect due to chemical reaction between the contents of the pipe and the pipe material. So due to chemical reaction, the pipe also elongate, and we also can take this into account. We have a special factor for it in the software. The next feature is the Young's modulus, also it called creep modulus for thermoplastic piping systems, depends on service life. As greater the service life, as lower the Young modulus. And also it depends on the temperature, and also it depends on the stress level. As greater the stresses, as lower the Young modulus. Okay. In steel piping, it depends only on temperature, but for thermoplastic, it also depends on service life and depends on the stress level. This is the main feature of the thermoplastic piping systems. The next feature is that in operating condition, the average creep models used, for example, for steel piping, we use the elastic models at the temperature, working temperature. For example, if operating temperature is 100 degrees, we use elastic models, Young models at 100 degrees. But for thermoplastic piping, we calculate two elastic models at 100 degrees, for example, and at 20 degrees, and then take the average value between them, because we assume that the temperature distributes through the pipe wall, not non-linear. So the distribution of the temperature through the wall is not linear like in steel piping systems. The next feature is Poisson ratio. It is highly dependent on the temperature. So Poisson ratio also depends on the temperature. For example, for steel piping systems, the Poisson ratio doesn't depend on the temperature. It is the same for all temperatures. But for thermoplastic, it's different. And in Staprov database, you can define different Poisson ratios for different temperatures. At the high temperatures, usually its value is 0.5. And the next feature is that allowable stress for plastic piping depends on chemical resistance factor, safety factor, and joint strength factor. Now, let's see how Staprov perform stress analysis. How to do this? You just select, you just draw your piping system and select the material. In Staprov database, we have a different material, different thermoplastic material, and Staprov just use it for calculation. So the procedure is almost the same as for steel piping system. Let me show you now the failure, some examples of thermoplastic piping failures. For example, this is the PVC piping, polyvinyl chloride piping system, which was failed. Fortunately, it was water inside, so you see the water flows out of the pipe. And here, after analysis, we see that we had a crack here. You see, this is the crack. This system was designed without any stress analysis, and after that, the owners of this piping system performed the analysis using Staprov software and found that we have the problem with this pipe with crack. Staprov show it with red color, and we determined that it was caused by the torsional moment like this. So this pipe expand here and push this leg here and produce a torsional moment around this pipe, and due to this torsional moment we have a crack here. This is another example. This is the PE100 piping system, pipeline. It's very long pipeline between cities. The supports was like this. You see it's the brick with support connected to it and connected with the clamp to the pipe. And the problem was that the lateral movements of the pipe was very huge, so it moved for several meters in lateral direction, and some of the supports overturned, like you can see here. You see, some of the supports overturned, and here. So we performed analysis of this piping system in Staprov software because it was designed without any stress analysis. This is the main problem, that a lot of companies design thermoplastic piping systems without any stress analysis. And after the failure, they try to understand why it happened. So here we found the problem that how to say, it was built at the summertime, but at the winter time the supports overturned, and we determined that due to stress analysis, that displacements in the at the areas where pipe turns, where is the bend, the displacements in a lateral direction is very huge. It's about in some places it's about 2 or maybe 3 meters, so it's huge displacements. All this is caused by the great thermal expansions of this pipe, because the P100 material expands 20 times greater than steel piping system. So if this will be the steel piping, the lateral deformations will be not so huge, but for plastic piping it's very high, and all supports overturned. So the idea was that we need to change the design of the supports to allow this pipe to slide in about 3 meters in both directions. Or another idea is to add some expansion loop here to reduce the great thermal expansions of this pipeline. And the next example is the thermoplastic piping system. It's process piping made of the PE100 material, polyethylene 100. Actually, the DVS code 2210, which is implemented in Staprov software, it allows analyze only simple piping systems like this. It's L-shaped loop, Z-shaped loop, and U-shaped loops. But we need to analyze the complex piping system. So that's why we expand the equations of that code to support analyzing any complex piping system like this. I can show the example. For example, this one, this system. So this is the P100 process piping system. Looks like this, and you can see its thermal expansions. Let me show you the animation. It is already analyzed, so I just can show you the thermal expansions. You see, this is the thermal expansions of the piping system. We can check the values. For example, click here. It's about 64 millimeters. And of course, we can check the stresses. It is an output pipe stress table. This is the stresses from the primary loads. It's weight and pressure loads, primary and secondary loads, pressure, weight, and thermal expansions. And the same in the cold state, when pipe is cooling down from the hot state. Okay, it's another example. It is the PE100 ship ballasting system analysis, and it takes into account the pressure, weight, thermal expansion, and also ship hog and sack, and also wind loads. I also can show you this model. It is already analyzed because analysis is not fast. It takes about 1 minute. So we will not wait 1 minute because I already performed analysis, so we can just see the results. Okay, so let me show you the deformed shape. This is, we have only two operating modes, it's hog and sag. So you see the deformations from hog and sag. Because the ship desk deforms and the piping system also moving, so we can check the stresses in our thermoplastic piping system. Okay, so this is just examples of some piping systems which was analyzed in StarProf software. Okay, so how we calculate stresses? According to the DVS code 2210, the stresses calculated using the following equations. We use the same equations, but written in some different form, because this code, for example, how to say it, assume that, for example, thermal expansion stress is calculated for a fully restrained pipe, but in fact it can be not restrained, so we calculate it more accurately. We calculate the real axial force and calculate the real axial stress caused by this axial force, including the Bourdon effect, including the thermal expansion, and including of axial force from some how to say external loads on the piping system, and also the bending moment. Also we calculate the torsional stress, and after that we calculate the equivalent stresses in the thermoplastic material. Also, we should take into account the piping expansions. We calculate expansions from three factors. The first one is from thermal expansion. We calculate it like thermal expansion factor multiplied by the temperature difference, also multiplied by the special temperature range factor, which is taken into account the nonlinear temperature distribution across the wall of the pipe. This is the first factor. The second factor is the pressure elongation of the pipe. It is calculated using this equation. It's pressure elongation of the pipe. It also automatically taken into account if you define some pressure in piping system. StarProf will take into account this elongation automatically. And the third is the elongation caused by the swelling effect due to chemical reaction between the pipe and contents. To take it into account, you should define this factor in the pipe properties. The pipe manufacturer should provide you this information about the elongation due to chemical reaction between pipe contents and pipe material. According to the DVS code, it is also calculated using the same equations. What is the temperature range factor? Temperature range factor take into account the nonlinear temperature distribution of the temperature through the wall thickness. For example, this is the pipe, this is the wall thickness, and the temperature distribution is not linear. For example, for steel piping systems, usually temperature is the same on the outer surface and the inner surface, but for thermoplastic piping, the distribution can be different, like this. So we should take into account using this temperature range factor. And there are some recommendations how we can take it. You can check the help system of StarProf which values you can use for this factor. The next feature is that DVS code developed for design of some standard piping layouts like L-shaped loop, U-shaped loop, Z-shaped loop, but we need somehow to analyze some complex piping system which is different from just L-shaped loop. So we expand the code equations, so we calculate the stresses, but it uses the same rules as this code, but for any complex piping system. So how we calculate the allowable stresses? The allowable stresses calculated the special characteristic equation, and it's stored in the database of the StarProf software. Let me check just a moment. Yes, I will tell you about how we calculate it a little bit later. Okay. Another feature of thermoplastic piping is that elastic modulus, also we call it creep modulus, is different. For example, if we calculate just stresses, for example, sustained stresses or operating stresses or cold stresses, we use this with creep modulus. How we calculate it? We calculate the creep modulus at the service life. So, for example, if our service life is 50 years, we take the creep modulus at 50 years. This is the database in StarProf of creep modulus, and it depends on the number of hours or years. So StarProf take the values from this database for 50 years, and also it should be at operating temperature and at operating stress. And we calculate this elastic modulus, also called creep modulus. If we calculate the loads on the supports, we calculate different creep modulus. We take the service life equal to 100 minutes. It is equal to 1.66 hours, this value. So the loads on the supports calculated using different creep modulus. For example, the creep modulus at the service life of 50 years can be several times lower than the creep modulus at 100 minutes. So if we calculate a simple piping system like this, the loads on the supports, if we take the service life 50 years, will be, for example, 10 tons. But if we will calculate it for 1.66 hour, it can be, for example, 30 tons. So the loads on the supports will be much greater at the beginning of the service life of our Python system, and it will become lower and lower upon a time. So after 50 years, the loads on the supports will be very low. But we need to take the maximum loads on the supports. In this case, we should use another creep modulus at 1.66 hour. Okay, and the third elastic modulus that we use in analysis, it is the elastic modulus for occasional stresses like wind, seismic, water hammer loads, slug flow loads. So for some loads which are very quick, which applied and removed very quickly from our piping system. So in this case, we need to use the dynamic elastic modulus at 0.1 hour service life, this value, 0.1 hour. It equal to 10 minutes. In this case, the elastic modulus will be much greater than elastic modulus at 100 minutes and of course much greater than elastic models at 50 years, for example. Let me show you the database in StarProf. This is the material database, material library. I open this library and I select some material, for example, PE100, this one. We have different type of materials here. Of course, you can add your own material, but we have some predefined materials. For example, PE100. I click Show. And here we see the data used for calculation of allowable stresses. This is the values of the thermal expansion factor, depends on the temperature, and Poisson ratio also depends on the temperature. And this is the creep modulus. This is like elastic modulus for steel piping, but it's called creep modulus for thermoplastic material because it depends on the time, on the service life. So this is 0.1 hour used for occasional loads. This is 1.66 hour used for support loads. And this service life used for calculation of the stresses in the piping system. So you see the values depends on the temperature. This is the temperature. It depends also on the stress level. This is the stress value. As greater the stress, as lower the elastic modulus. You see, at lower stresses, the elastic modulus is greater than the elastic modulus for greater stresses. And also, it depends on the service life. You see, for example, this one, it is at service life 10 minutes. This is at service life 100 minutes. 100 minutes. This is the 10 minutes. And this is, for example, H1000 hours. It's much lower. It's about, if I'm not wrong, it's about 10 years. Maybe I will check later. Okay, so this is the value. And at H100, H8700 hours, it is much lower. Like you can see here. Let me check how many years. Yes, this is, sorry, it was 1 year. This is the 10 years. This is the 25 years and 50 years. So this is the table of creep models for different temperatures, different service life, and different stress level in our piping system. So StarProf automatically takes all this data and use it in analysis of the piping system. So if you need to add some new material, you need to fill all this data. For some materials we have it, but for some materials we don't have it. In this case, we use more simple tables. Let me check. I'm not remember. For some materials we don't have all the scope of information, so we use much smaller tables because there is no any more information. But for some materials we have a lot of information. For example, polypropylene PPB. Also we have all required information. Okay. So actually, if you check the DVS code, it requires this, and also there is the Simona engineering guide. Simona is the manufacturer of piping, which is famous and widely used in Europe. And it has the engineering guide how to analyze the piping, thermoplastic piping systems. So some of information was taken from this engineering guide of Simona catalog, and also there is some test examples, and we compare it with StarProf, and also it shows a good good match between Simona calculations and StarProf calculations. So this is how it requires to take the elastic models here. And another one is how we calculate the allowable stresses. So this is the equation for allowable stress calculation in DVS code and also in Simon Engineering Guide, and how we use it in StarProf software. So you need to define the safety factor in StarProf software, the chemical resistance factor. Also, you need to define the lane conditions factor. For example, for above ground, underground piping, it's different. 0.h it's for underground piping, buried piping, and 1.0 for above ground piping. And also the strength of weld joint. It also can be different. How we calculate the basic allowable stress value, this one. We calculated this using the special characteristic equation. Let me explain. This is the allowable stress for polypropylene piping systems. Just for example, it was taken from EN code, this one. And this is how it looks like on the graph. That diagram can be approximated using the following two equations. One equation for the left curve, this one, and one equation for the right curve, this one. So this is the left curve and this is the right curve. And as you can see here, the scale in horizontal direction is logarithmic. It's logarithm. So this is the service life in hours, and this is the allowable stress, vertical direction. And also it depends on the temperature. For different temperature values, we have different diagrams. And that diagrams approximated by the following equations. And in this code, in EN code, you can find the factors A, B, G, and J for these equations. So you need to define it here, A, B, G, and J. You should enter it here. For some materials, we already done this. For example, for polypropylene, PE, PP, PVC, and some other materials. The information already stored in the database. And this is the values of that factors for different materials. For PE material, PP, PVC, and also we have for some additional materials. For some materials we use both curves, left and right, but for some other materials we use only one curve. It depends on the code and on the material. So sometimes we use one curve, sometimes two curves. And also here you can see the DIN code, which also contain such a characteristic equation and values of the factors which is used in this equation. So you can compare it with StarProf database. You see the values are the same for PPH material, for example. And that values is equal to this one. Okay. So how StarProf calculate the allowable stresses? They calculate the basic allowable stress depending on temperature, service life, and only temperature and service life, sorry. Okay, so we calculate the value of allowable stress, and after that we'll multiply it by the several factors. The KY, it's safety factor, this one, safety factor, this. KC, joint strength factor, Kx it's chemical resistance factor, and Kp lane condition factor. In Staprov help system, you can find description how to define that factors, which values you can take to analyze your piping systems. So it's just additional safety factors. It is used for primary loads, only for sustained stresses caused by the weight and pressure loads. But if we will add the secondary loads like thermal expansion, support movements, cold spring, and some other secondary effects, in this case we add additional two factors. It's Kt and K cyclic. It's additional safety factors for secondary loads. In DVS code, there is no information about the self-balanced loads, KT factor, but in fact, for example, we take it from the Russian Ghost code, in which we have such KT factor for secondary load, because, for example, if you have a polyethylene piping system, PE piping, from the secondary loads, it can deform slightly and self-balance the expansion stresses inside your piping system. So it will not damage your piping system. In this case, we apply some additional factor, which is greater than 1.0. And for thermoplastic material, PE, it is 2.5. But you will not find this information in DVS code. So if you want strictly follow the DVS code, you should apply here, open the Staprov database and apply 1.0 value here. But it will be too conservative. The experience shows that we don't need such conservativeness. So you may leave 2.5 value if you don't want your piping system to be too conservative. But for weight loads, we should use this factor equal to 1.0. So weight loads are not self-balanced, but secondary loads are self-balanced. We can use some increasing factor for stresses. And the second factor is fatigue factor. It takes into account the multiple cycles of the load. And this is the equation. How can we calculate it? It's 4 divided by the number of full cycles in power of 0.2. And it should not be greater than 1.0, and it should not be lower than 0.4. And Staprov just multiply the allowable stresses by this factor. Another feature is calculation of the stresses in the test state. For the test state, we assume that all the factors, let me check, just a moment, this one, this, and this equal to 1.0. So we take into account only one factor, is Kc. It's a joint factor. Only Kc factor is not 1.0. All other factors are ignored in test state. And also the basic stress for the test state is calculated for the service life equal to 24 hours. So we use greater allowable stress for the test conditions, hydro test or pneumatic test. And for occasional loads, for example, wind loads, water hammer loads, or some other loads, we also use the special allowable stresses. We also exclude all the factors. So we remove them, remove all the factors, and we calculate the basic allowable stress at 24 hours service life, but at the operation temperature. For the test state, we calculate it at test temperature. Usually it's just 20 degrees. But for occasional loads, we use the same equation, but for operating temperature, it will be a lower value. The allowable stress will be lower. And how we calculate the stress intensification factors. We calculate it using the following equations. For the bands, we use the following equations for flexibility and stress intensification factors. For straight T's, we use the following equation. For reducing T's, the following stress intensification factors, and for reducers. But actually, some users of software are required to use their own stress intensification and flexibility factors. So in the latest version of the StarProf software, which will be released in approximately 1 month, we add ability to define custom stress intensification and flexibility factors. So it will be allowed to enter any custom values of stress intensification factors and flexibility factors in current version and current official version. The stress intensification factors and K factors calculated automatically using the following equations. And also, this is important to check the buckling of such thermoplastic piping system. But at this moment, StarProf doesn't perform buckling check, the stability analysis of the piping system. We plan to add such checks later in future versions. But I pay attention that this is also important, and you should check the buckling. The first one is the buckling caused by the negative pressure. For example, if you have vacuum piping system with external pressure, in this case it can buckle. So you need to perform this check. It's quite easy, quite simple equation, and you can find this equation in Simona engineering guide. There is no information in DVS code, but the Simona engineering guide is very famous, and it is not the code, but there is very important information on how we can analyze such systems, including the buckling checks. So this is how we check buckling from external pressure. Also, we should check the buckling caused by the axial compressive load. For example, if you have the buried pipe, a very long buried pipeline, it will be compressed due to thermal expansions, and it can buckle due to high compressive load, axial compressive load. So you should perform the following check. You can take the axial load from the StarProf software. It's quite easy in internal forces table. You can take this value, and after that you can manually check the stresses. In future versions, we plan to add the automatic check of that loads. Also, you can just take the axial stress in StarProf. Actually, StarProf provide you this information. If you open the stress table, you can put your mouse over any cell, and StarProf will provide you the equations, how it calculated the stresses in your piping system. So you can take some values from here. So for example, you can take the equivalent stress, bending stress, or any other. Okay, so for example, here is the axial stress value, and you can compare it with the allowable stress for the buckling check, or you can take it from the table with internal forces, from internal force table. Okay, so now how to close it. Okay, so now let's check another feature. Is for example, you have some new material which is not included into StarProf software. For example, it can be some custom material by some manufacturer. So you should ask manufacturer to provide you the values of A, G, B, and J factors. But if they can't provide you that values, you can calculate it using the Excel. We have a special Excel file. It is included into my Udemy course. It's the course on Udemy. You can download this Excel spreadsheet. So you can enter here 3 points, first, second, and third, with different temperatures, for example, 60, 60, and 80 degrees, and different service life. And enter the allowable values for that 3 points. After that, after calculation, you will receive the A, G, and B factors. So if you have the diagram, let me show you the diagram like this. You can just take three points from this diagram, first, second, and third, and this is enough to calculate that factors for the characteristic equation. And this is the test results. There is some examples in the Simon Engineering Guide. According to the DDS code, they calculated the allowable stresses according to the DVS code. And also we calculate the same stresses in StarProf, and you see that we receive the same allowable stresses. Some customers of StarProf required us to provide some verification examples, so we did this work, and we received the same results as in Simon Engineering Guide calculations. And also there is another allowable stress. As you can see, it is the same as in StarProf. And there is another example. Also, we calculate the allowable stresses, but actually we found some mistake in example of Simon Engineering Guide. In StarProf, the allowable stress calculated more accurately. Without how to say, they just round some values, but in StarProf we calculated more accurately. Okay, so but it's approximately the same values. And this is the wall thickness. We calculate the wall thickness. You see almost the same value. Also, there is some error in example of Simona, so we calculated more accurately in StarProf. So in start elements procedure, you can calculate the wall thickness for thermoplastic piping. Let me show you. Just a moment. We can calculate the wall thickness. How to do this? You just open StarProf software, and let me show you from the beginning. You click File, New. If you select piping, you can define any 3D piping system. But if you select Elements, you can select the code here. It's DVS code, this one. And okay, and you can calculate the wall thickness. So you can define some diameter of your pipe, some temperature, the factors, different values of factors. Select the material, for example, P100, service life, for example, 50 years, the pressure, for example, 1.5 atmosphere, and you can calculate required wall thickness, 15.2 millimeters. If you change the service life, you will receive different wall thickness. So you see it depends on the service life of your piping system. And how to create any complex piping system. To do this, you can click here, File, New, Piping, and select the DVS code for the piping, for the thermoplastic piping system, this one, DVS code. Define the ambient temperature, test temperature, and some other parameters. I will not explain them all. You can find that information in my training course. It's about 25 hours of video. Okay, and now you can draw your piping system. I will just draw the very simple U-shaped loop piping with some supports. So I create the pipe, for example, it will be 20 meters. I don't remember the standard diameter, so I will just use some values. For example, this is the wall thickness. I select PE material, the pressure, for example, 1 atmosphere, temperature, for example, 40 degrees, test pressure, for example, 1.5, and fluid weight, fluid density is 1000. It is the water. And some additional properties here, for example, pipe lane, it will be above ground pipe, so lane condition factor 1.0, swell and strain it's 0. We will not have any chemical reaction between the plastic and water, and all other factors I will leave 1.0. Okay, so this is my pipe. I add anchors, one anchor here, one anchor here, and I add the node in the middle of this pipe. In this node, I will add the expansion loop, for example, 2 by 2 meters with 90 degrees, like this, and I will add bands. Let me save my model. I will save it. Okay, so I will add the bands. You see it's gray, but if you will click here, you'll see different type of bands. That's because not all the bands available for plastic piping. Only meter band, smooth band, and latch radius bands are available for thermoplastic piping. I will just use this one. It's just smooth band, define some radius of the band. It can be made from different materials, even from steel material also. In this new version, we also allowed to define manually the stress intensification factors, but I will not use this feature right now. This is the chemical resistance, swell and strain, and some other properties. So I will not define anything. I will leave default values, click OK. After that, I can copy this band or use Ctrl-C and Ctrl-V here, here, and here. And also I need to add some supports. Let me add support here on this pipe in the middle. I add the node, and after that I add the rest and support. The friction factor 0.3, but actually for rest and supports for thermoplastic material, the friction factor should be lower. Let me check which value we can take here. I'm not sure. There is no value, but I think it's something about 0.1, maybe 0.15, something like that. You need to check the literature. Which friction factor should we take? Okay, and after that, I will add some supports on this pipe. I will use this feature to add several points. I think the distance between supports should be very low, so I will use 1 meter rest and support. 1 meter, and the same here, 1 meter. And we finished, so we can now run analysis. I click here, run analysis, and we can check the output 3D view and see the animation. How does it work? So this is the thermal expansions. Left position, it is the installation state. The middle position, it is the operating state, and the right position, it is the cold state after cooling down from the hot state. The pipe never returned to initial position, to the installation state, because of friction, because when pipe cooling down, the friction doesn't allow the pipe to reach the installation state. So we have three states here: operational, installation, and cold state. And of course, we can check the stresses. Everything is okay here. All the stresses within the allowable limits. And we can check the stress table, output pipe stress. And here you can select the operational mode. We have two modes, operational mode and test mode. As you can see, the allowable stress in operational mode from the weight loads, it's about 50 atmospheres, 50 kilograms per square centimeter. We can change the units. Let me change it. File, customize units. I will select MPa. Okay, so now it's about 5 MPa, and the stresses from primary and secondary loads is about 12 MPa, and for cold states about 20 MPa, and for test state it is about 13 MPa allowable stress, and from primary and secondary loads it's about 32 MPa. Of course, we can add some how to say, occasional loads, additional. Let me add some additional forces. For example, in some point, I can add some additional force in y direction. For example, 500 kilograms, and we can analyze this system and check the deformations. This is operational mode. This is operational mode with this additional force. I add to great values, so we have a great deformations of our piping system. And we can check the stresses. Output stress. This is the operational mode, and this is the mode with this additional force. You see here we have calculated stresses much greater than allowable stresses. Okay, and also we can calculate the restraint loads. I'll remind you that restraint loads calculated using different elastic modulus at different service life. So for stresses, we use creep modulus for the 50 years, this value. That values we use for stresses, but for loads on the supports, we use elastic modulus for 100 minutes. And for occasional loads, we use greater elastic modulus for 10 minutes. Okay, so this is how Staprov perform analysis of the thermoplastic piping system. Of course, you can change material. For example, you can select all the piping and change material. For example, you can select PP-B, polypropylene B. And also the same you can do with all the bands. You can change it to polypropylene. Okay. And that's all. So you can run analysis again and check the stresses. So this is the stress for the polypropylene material. Also, it passed the strength requirements. You see, everything is okay. Okay, so now also I want to inform you that we have a free 30-day trial of a StarProf license. So you can open this website and just download StarProf software. Just click download. After that, you can run the software and you will see small registration form. You type information about your company, and after that, your free 30 days trial will be activated. You can use the software without any limitations. The only limitation is the time, 30 days. So you can use everything from the top of my head, including the HDPE piping system, but I'm not sure. I need to check if it's included into trial version or not, but I think it's included. So you can use all the ASME code and DVS code for thermoplastic, also for fiberglass piping systems. And also this is the training course which cover the thermoplastic piping systems, fiberglass piping systems, steel piping systems, some information about dynamic effects, static analysis of a piping system, and a lot of theory. So if you want to participate this course, you can take a shot of this discount coupon code. Also, I can copy it into the chat. I can copy this link and copy it into the chat. Just a moment. So you can save it on your machine. Sorry, I'm not sure. Okay. So this is the discount code. Copy. Okay, so I copied it into the chat of the Teams. And now I can answer your question. I see you have some questions. I will read it from the top to the bottom. I'm not sure if you see that questions. Okay, I will just read it. How do you compare this software with Caesar 2? Actually, as Caesar 2 is a standard de facto in some countries like India, United States, Europe, and some other countries, the StarProf is also standard de facto in Russia and some other related countries. So, for example, in Russia, we don't use Caesar 2 software. We use only StarProf software. It covers about 95% of the market, and we have more than 2,000 companies who is using it. And it fully cover all the requirements of all industries. So this is very famous software, and it has the history 20 years greater than Caesar 2. So, for example, StarProf was developed in 1965. The Caesar 2 was developed in 1985. StarProf is has longer history and more experience. But it was translated into English language just maybe 10 years ago, and we entered the worldwide market too late. That's why Caesar 2 is well known in all other countries, but StarProf is not so famous. But actually, it covers all the abilities of Caesar, and I'm developer of the StarProf software, so I can speak is it better or not, but I can just say the words of our users that this software is much easier and more comfortable to use than Caesar. So, but it's up to you. You can try and you can have your own opinion. Okay, so you can use this free trial version and check yourself. Also, we have a training course. You can see all the abilities of the software, and we have a lot of YouTube videos. Okay, the next question is Waterheimer considered? Yes, it's considered, but as I said before, we use the special PAS hydro system software to calculate Waterheimer loads. Just a moment. Here, this is PAS hydro system software. It can be also found on our website. You can also download the trial version of hydro system. And the advantage of StarProf is that it integrated with all that software like Nozzle FM. This is analog of Nozzle Pro. I know that most of you know that which is Nozzle Pro. So this is the same, but it's fully integrated with stress analysis software StarProf, and also it is free software for StarProf users. So if you buy StarProf, which is already about 4 times cheaper than Caesar 2. Also, you will receive Nozzle FM for free. So it is great advantage. And also, of course, you can calculate the Waterheimer effect if you will buy also the hydro system software, which is also integrated with StarProf. We have information about this integration and video how to use it on our YouTube channel. If you want, you can find our YouTube channel on our website and watch the videos, okay, for more information. The next question is, please share the presentation after meeting. Anup, can I share the presentation or you will do this? Please answer, because I need
will
your
share it.
approval.
Please send me a WhatsApp message and I will forward that to you. I am sharing my WhatsApp number in this chat.
Anup, I already shared the presentation with you using WhatsApp, so you
Right,
can.
right, right. So whoever is required, they need to send me a personal WhatsApp message and I will share with them.
Okay, okay. So yes, you can contact Anup and we will share you the presentation. Okay. So the next temperature range factor, how we are defining vendor providing. Yes, vendor can provide, but in some codes you can find its value at 0.85. 0, where is it? Sometimes it used like 0.85, sometimes it used 1.0. It depends on manufacturer requirement. Yes. And actually it depends on the thermal properties of the material and the wall thickness. The next, for ballast system analysis, external load will be provided as submerged inside water. Actually, the example which I show you with ballast, with ship ballast in system. Let me find it. Where is it? This example, it is how to say, it is not underwater piping system. It is on the ship desk above the water level. So it is on the air. It is not submerged piping system. Uh, the next question, how service life is defined? Let me show you. Service life defined in the project properties. So you open project settings, and here you can define the service life. For example, here is the 20 years. Let me show you this. Let me make a screenshot. This is the stresses. This is the stresses for 20 years, and we can change it for 50 years. Oh, sorry, here, 50 years, and analyze it again, and check also the stresses, so we can compare them. Just a moment. Okay, we can compare. You see that allowable stresses are lower for this is the 50 years, and this is the 20 years. The allowable stresses are different. You see, different values. So service life is defined in project settings here. Okay, next question. Is it ISO standard also covered for material? I'm sorry, I'm not fully understand your question, but if your question is for ISO standard for fiberglass piping system, if we have material properties, then yes, we have. For example, you can select the ISO code. Where is it? Just a moment. Here is it, the ISO code for GRP piping systems. If you create the pipe, you also can select the materials, but we added only the most famous manufacturers in the world. It is the Future Pipe Industries, very strong pipes. It's Bond Strand, Fiber Bond, and some other materials. But of course, you can add your own materials into database for GRP piping systems. You can just click add some name of the material and define the properties of this material. You can add the properties at different temperatures, add the failure envelope properties provided by manufacturer, provide the elastic modulus in axial and hoop direction, shear modulus, thermal expansion factor, Poisson ratio, and JXX factor for it take into account the changing of properties of material upon a time. So it depends on service life also. And the cyclic factor is used here. So all the information stored here. If you fill all this data, you can work with your piping system like with steel piping. So you can quickly change material. For example, you can draw your piping and compare which material will be better. For example, you can check the PE material, PP material, you can check the fiberglass material, you can check steel material and compare them and see which material will be better for your piping system. And you can do this quite quickly in 1 hour. For example, you can compare different materials. For example, for this ship ballasting piping system, this one, we compared several different materials to find which one will be better for this piping system. We compared with the fiberglass material and different type of thermoplastics and found that the PE 100 is best for this piping system. But of course, the design will be different for different materials because we have different allowable stresses, different thermal expansions. So design will be slightly different. The next question: what are the differences between FRP and HDPE pipe stress analysis? Can we use ISO for HDPE pipe stress analysis? Actually, I think the answer is yes. Yes, we can use ISO code for HDPE pipe stress analysis, but we need to perform tests required by the ISO code. So manufacturer should provide tests with such pipes and find the properties of this material. So we should provide you the failure envelope. They should provide you the elastic models. But depending on the service life, you should define different properties of material. For example, you can create material, for example, PE material for example, 10 years, PE material for 25 years, PE material for 50 years, and PE material for 100 minutes, and PE material for 10 minutes. So after that, you perform analysis for 50 years, for example, and use 50 years properties and check stresses. If you want to check the loads, you need to use another material. And if you need to check for occasional loads, you need to use another material. So you will have to perform several analysis of your pipe and system with different materials. Using the DVS code is much more comfortable because you just create one model, run it, and StarProf will perform analysis according to all the requirements of this code. So it's possible, but it's not so easy. But yes, it's possible. And also you need to get the properties of that material. It's also not so easy to fill the database. So it will consume a lot of your time. The second question, HDPE pipe is usually considered non-critical. So can we proceed using HDPE pipes by following manufacturer's guidelines without pipe stress analysis? Yes, in in most projects, the HDPE material considered like non-critical, but the failures is quite often. So we have reports from different companies who had the problem with plastic piping system, and all that problems was caused by the absence of the stress analysis. So my opinion that if you want to avoid the problems with your plastic piping systems, it's better to perform stress analysis. The main failures can for rigid materials like PP, like PVC, PP, the stresses can be critical. For polyethylene piping systems, PPE, the displacements can be critical. So to check the displacement, you also need to perform the stress analysis somehow. So maybe it's not critical, but the problems are quite often with such systems. So I recommend to perform stress analysis. Another question, it is the third question, is it possible to analyze the combined system, for example, part HDPE and part steel? Yes, it's possible, and I explained it in my training course. Let me quickly show you how to do this. For example, we have the following system. It's quite easy, actually. We have the following system. Let me delete this note. For example, this part is the steel piping, and this part is HDPE piping. And we have, for example, some flange here, some flange connection between that pipes, like this. Okay, so how to do this? I define the line, and I will call it steel. Another part, I will also define the line. I will call it PE 100. I can define some color for them, like this. So this part is steel, and this part is polyethylene piping system. So now how can they analyze it? I run analysis of I select this part, open the properties, and change the material to the carbon steel. Actually, it is the special material we added, carbon steel plastic. Actually, it has the elastic modulus equal to the carbon steel elastic modulus, and thermal expansion, Poisson ratio equal to the steel piping, but it is defined in the plastic code. Okay, in plastic code database. So we defined this, that this part is steel piping. After that, we perform analysis. We can check the thermal expansions, for example. This is the thermal expansion of the steel piping, and this is deformations of the HDPE piping. And they influence each other. So we have some loads transferred here, some loads here. So now how we can check stresses? Very easy. We just hide the steel piping part like this. I uncheck the lines for steel part, and it will disappear in stress table also. So if it's visible, you will see the stresses in steel part also. But if you uncheck it, you will see stresses only in the plastic part. Okay. After that, you can make the reports. For example, make report into Microsoft Word and provide all the reports for the plastic part of the piping system. After that, you save your model. You open this model again and change the code to the steel piping. For example, ASME B31.3, like this. After that, you show this line and you hide the PE100 part. And for this part, you define the material, for example, A105, this one. But also you will have to add in the database, you will have to add some material for plastic part. You need to take the elastic modulus from the database or from the plastic database. So you will have to do some manual work to add the elastic modulus, the same at the certain service life and certain temperature of your plastic piping system, and define it here. After that, you can hide it and run analysis. Let me add stress range. Okay, so now we can run analysis. Oh, sorry. Let me define. I don't have right now the required material, so I will define the A105 material for all the piping system. Oh, sorry. Okay, like this. Okay, and now I can run analysis. Oh, sorry for the bands also. But actually, I should not use A105 materials. I need to define the custom material. But I don't want to spend the time for it. And let me check. Where is it? Oh, sorry. I broke something. Okay. So now I run analysis, and after that, you can just hide the plastic part. Hide the plastic part and check stresses in steel part of the piping system. So it's quite easy. Some customers of StarProf performed analysis for free from piping system which had free materials. It's FRP, PE material, and carbon steel. Free materials in one model, and it's just connected with flanges to each other. So it's possible and it's quite easy. Okay, next question. Do we need to define various load cases similar to Caesar2? Actually, it's one of advantage of StarProf. We work with not with the load cases. We work with operational modes. For example, first operational mode, you just define the pressure, temperature, weight of the fluid, insulation weight, and some other properties. And this is the operational mode. When you can define the second operational mode with different pressure, different temperature, different different fluid date and other properties. and so on. So you work with operational modes, not with load cases. But load cases created automatically by the software. So when you add, for example, let me show you, this is the load cases for the first operational mode. So this operational mode and that load cases are hidden inside this operational mode already. It is done automatically. So if you will add, for example, wind loads, firstly, you need to define them here. Just a moment. In project settings, if you define some wind loads, for example, let me add free wind directions. Okay, first, second, third. It can be any number of wind directions. Okay, and just a moment. I will add some data. Okay, so if you open the operational mode editor, for example, if you will not define the wind, you will see 6 load cases. If you add the wind, you will see much more load cases which created automatically. If you add snow, seismic, you will see much more load cases. And all that load cases are hidden, hidden inside the first operational mode here. And the same with all other operational modes. So it's a different idea, not the same as in Caesar. And it's quite hard to understand for Caesar 2 users. For beginners, it's quite easy to work with StarProf, but for users of Caesar, it's not so easy to change their mind because they used to work with Caesar, used to create load cases manually. So it's hard to understand how to work with software which doesn't require to define load cases manually. But some users of Caesar adopt and they can use it quite easily. But you need to spend some time to change your way of thinking when you work with StarProf. In my Udemy course on Udemy, you can learn about the difference between load cases and operational modes in StarProf. So operational modes is quite much more easy. Okay, and the fifth question, can we use different codes in the same model? I already answered. Yes, you can do this. You can use DVS code with ASME B31 free. You can use ASME B31.1 with B31 free. And for example, in Caesar, you can define different code for each part of the piping system. For each pipe, you can choose different code, but this approach will work only if load cases for each code are the same. But if load cases for each code are different, this approach will not work. So the approach which I told you right now can work with any codes, with any load cases. For example, HDPE piping code and ASME B31H and maybe European code have totally different load cases. Some codes have safety factors. For example, weight loads multiplied by some safety factors. In other codes, the weight is not multiplied by safety factors. So the approach that I told you right now can be used for combination of any codes with any requirements of load cases, of safety factors for loads, and so on. It's not just choosing of different codes how we calculate stresses, because in different codes the support loads also will be different. For example, if you apply some safety factor for weight loads, you'll receive different loads on the supports. In some codes which we have in StarProf, some codes require this. And it is not just changing the way of calculation of stresses. It also the way of calculation of load cases, okay? Is there dynamic analysis course in yours? Yes, in this training course, we also have uh, information about the dynamic analysis here. The next, the copy of presentation, okay, it's for Anup. Can you provide us attendance certificate? I don't know, Anup, maybe you can answer this question about the certificate.
Yes, if you need the attendance certificate, same way you can send me WhatsApp message. I will forward that to you after preparing.
Can you provide the recording? It's also a question for Anup.
Yes, that is also recording. Normally we upload after 1 week, so it will take some time, but we will inform you once it is uploaded.
Okay, and next question. Which is default code to be considered for allowable stresses for HDPE piping? DVS, GHOST, EN. Actually, the GHOST and DVS and EN use the same approach, so it follow all the three codes. And is this software have bidirectional interface with famous CAD softwares? Yes, of course, it has bidirectional interface. Let me show you the external interfaces. We have external interface with Aviva. It is the, how to say, we don't use the PCF format, we don't use some neutral format. This is the direct communication between Aviva and StarProf. We use the special plugin for Aviva. You install the special plugin and it communicates with StarProf directly. So it transfers the data very accurately, much more accurately when using the PCF format files or any other files. And also we have interface with some other CAD systems using the PCF files, Isogen. Also we have a smooth and seamless interface with Pass Hydro system, of course, to transfer loads from Waterhammer, from Slugflow. We have interface with Caesar2 and AutoPipe. You can transfer the structural and CII file, Caesar2 neutral format file. You can open Caesar2 files and you can save Caesar2 files. Also, we have integration with Autodesk Civil 3D with Pass Nozzle FAM. It's seamless software. We have integration with LeCAD software for Lysaga Springs. We have integration with Excel. You can read, for example, pipeline route from the Excel. And also we have integration with AutoCAD. You can read AutoCAD files, you can export to AutoCAD, and we have the programming language interface. So you can write your own applications on C#, Visual Basic Net, and it can provide data for StarProf, run analysis, take some information back, and so on. So some of the interfaces, for example, interface with Caesar, Aviva, was created using this external interface. It was firstly created like external application for StarProf, and after that we just integrated this application, external application inside the StarProf. Some customers use Visual Basic for applications, which is included into Microsoft Excel, and they write some programs to integrate with StarProf. So integration capabilities is very strong in StarProf. Okay, so
And also just to add, I know some organizations in Egypt that use, for example, their organization asks them to use Scissor2 software as the final output reporting software. So what they do that as the cost of StartProp software is less, normally 1/4 of Scissor2, so they take one Scissor2 license or 4 or 5 StartProp license. They do everything, modeling and other things in StartProp. Then for submitting to client, they transfer the model into Scissor2, and that way they submit the final report to client using Scissor2 software. So that also you can do.
yes, Anu, thank you. They do this because StarProf is about 4 times cheaper than Caesar, so you can save your funds using this approach.
Sorry for asking.
Yes, now you can ask directly because almost we are towards the end of the session. So if anybody has any more questions, you can unmute yourself and ask questions, but once at a time, not 2 or 3% together.
Yeah,
Yes, Binod, you
okay.
can
Just
continue.
yeah, yeah. How we can compare this in Caesar? Whether HTP can be done in Caesar? Because I couldn't be able to find the steps for that. How you can say about that?
Sorry, can you repeat, please? I didn't catch
The
how we compare.
HDB piping. Yeah, yeah. HDB piping stress analysis. Now, same if I want to do it in Caesar, is the methods available to proceed in the Caesar? Anup or anyone can say about this because right now we don't have a stat pro, but if I want to do it in HDP in Caesar, is the methods available for that?
No, Caesar 2 does not have the capability to perform HDP pipe stress analysis.
There is no DVS code in Caesar. It have
Okay,
only Ask Me Before One free.
okay, okay. Because at on at client side, just we faced one issue for this HDB piping that we have informed them to check with the vendor. That's why I asked. In that case, that only the Stat Pro is the only possible thing, or whether any other softwares are there.
Autopipe is also there, but StartProp is much easier, I feel. Alex may give you more insights.
Yes, actually, how to say, if you compare the free softwares, Autopipe is easier than Caesar, and StarProf is easier than Autopipe. Actually, I'm not sure about the abilities of Autopipe related to the thermoplastic piping systems analysis. I'm not sure if it has some codes or not. I need to check.
They don't have various materials, but for P100 they can perform that, I know.
Okay, okay.
Okay. Suppose at in future, near future, if we face anything, just we can give a code for you so that you can perform those HTTP analysis. How about because I am at client side right now. Just if whatever maybe if is coming, just we are stuck somewhere about this. How about the opinion of?
Mr. Alex, have you got the answer? Question
I'm
means they want
sorry.
to perform. Okay, they want
He
you to
speak
perform the
too
stress
quick.
analysis. Okay, let me explain. Means Mr.
Yeah.
Binod wants your team to perform the pipe stress analysis and submit them a report. Means they don't want to purchase the software. They want you to perform the stress analysis and then submit the report to him.
Actually, it's possible, but usually we don't provide the service of pipe stress analysis. We are software developers. So if you need it for some verification, it's of course it's possible.
Okay, okay, thank you.
Any other question? Mr. Alex, I think nobody has any more questions, and thank you for continuously teaching us for more than 2 hours, around 2 hours, yes, and without any break also. So really thankful, and the session will be helpful for all, we believe. And if you have any final words, you can say that, and then we can close the session.
Yes, thank you for your attention, and have a good night. Thank you.
And thank you to all participants as well. Thank you. If anybody of you want the certificate as well as the PPT material, means PDF material, then please send me a message and I will forward those to you. Thank you. Good night. Bye bye.
Thank you. Bye,
Yes,
Anup
thank
sir.
you. Bye
Thank
bye.
you.